So you finished the experiment? Great! What's the result? What do you mean you measured 1,000 values? I don't want to see that. Give me just one number, the typical one. Yeah, we have to talk about that. The problem is, the typical value has no exact definition and it might not even exist for your application. But we can try to get close to it. Say we measured a few hundred values and plot the results on the x-axis. There are so many points that we can't see anything. But we can divide the x-axis into small intervals, and the greater the density of the values, the higher we pull them up. Since this is still a bit confusing, we can reduce and hide this complexity behind the bars of a histogram. We see that the density of the values is large somewhere in the middle and falls off more or less symmetrically the further we look to the left or right. Thus, we might conclude that the typical value is essentially in the middle of all measured values. We might have done another experiment where the measured values are concentrated in two distinct blobs on the x-axis. The middle is now somewhere between the two blobs. But since there are no measured values even close to it, it cannot be typical in any way. You may say that in this case there might be two different subgroups and that we should analyze each blob individually. And you might even be right, but the claim is not a proof. And even if we ignore this problem for a moment, where exactly is the middle? Let's look at the results of yet another set of measurements. Here, the distribution of the values is skewed with the tail to the right. Where should the middle be here? Halfway between the minimum and the maximum? But then more than half of the measured values would be below it. That can't be right. So the middle should be more to the left. But how far? In order to get a useful definition of the middle, as a substitute for typical, let's take a look at a smaller set of numbers. We will plot them against the measurement order to get a better view. Say we measured the following 7 values: 7, 6, 3, 4, 4, 7, and again 6. Now we can take a trial value for our middle, say x at 0.5. It is far below all measured values, so the distances to those values are all large. If we increase our trial value, the distances get shorter until it is somewhere in the middle, for example near 5. If we increase it further, the distances get longer again, so the middle should be where the distances are short. But which one of the 7 distances should we choose? Well, we want to be in the middle of all values, so all distances should be involved somehow. Unfortunately, there are infinitely many combinations of all distances, and each will give us a slightly different middle. One of the simplest possibilities is our first idea. Minimize the sum of all distances. Each distance in the sum is the absolute value of the deviation from one measured value to our trial value x. Minimizing this sum will lead us to the median. So let's scan all possible trial values. On the right hand side, we will plot the corresponding sum of distances. First, our sum decreases and has a kink whenever we cross one of our measured values. Eventually, the sum of distances has a minimum and continues to increase for even greater trial values. The minimum, called the median, appears at the trial value 6. Thus the median m in our example equals 6. However, is that minimum unique? And if so, how can we calculate it? Since our sum of distances has these kinks, it isn't smooth, so we can't just look for the zero of the first derivative. But we can do something similar, and like the derivative, it will have to do with the slope. First, due to the way we are scanning with our trial value, we are effectively sorting our measured values in a scanning order. What can we say about the slope of our sum after we have crossed k of the n measured values? If we know our sum for our trial value x, how much does it change when we increase x by a small amount delta x? Our sum increases by delta x for each of the k values we've already crossed, and it decreases by delta x for each of the n minus k values that we have yet to cross. Simplifying, we see that our slope equals minus n plus 2 times k. Now, before we have crossed any of our values, the slope is minus n or minus 7 in our case. After crossing our first value 3, the slope increases by 2 to minus 5. Because we have 2 4s and 2 6s in our list, crossing each of these values increases the slope by 4 each time, which first gives us -1 and then +3. After crossing all n values with our trial value, the slope becomes +n, which is +7 here. So we have a minimum where the slope changes from negative to positive. In our case, this median value is 6. If we have an odd number of measurements, the minimum is always unique. Why? Well, we start with a negative odd slope, but every change in the slope is a positive even number. Therefore, we can only have one minimum. But where is it? After crossing n-1/2 values, the slope is -1, so we're still going down. However, after the next value at index n+1/2, the slope is now +1 and we are going up. Hence we have just crossed the minimum. Therefore, for an odd number of values, there is always a unique minimum, the median, at index n+1/2. In our sorted list of measured values, this is just the number exactly in the middle. For an even number of measurements, however, things are more complicated. Let's assume that we forgot to write down our last measured value. That leaves us with the 6 values 7, 6, 3, 4, 4 and 7. Now we do the same as before and scan with our trial value. At first, everything looks fine, but then the slope becomes 0. Why? Well, for the 3 values we've already crossed, the distances increase at the same rate as they are decreasing to the remaining 3 values. Thus the sum doesn't change and has a slope of 0. After crossing the next value, the sum of distances increases again. Now we don't have a unique minimum. Any value where the sum of distances has slope 0 could be the median. Using the same ideas as before, we start with the slope of -6. After crossing the 3, the slope changes to -4. Since we have 2 4s in our list, the slope then changes by +4 to 0. After crossing the 1 6, the slope becomes +2 and finally +6. If the measured 6 had been a 4, the slope at 4 would have changed by +2 times 3 or +6, and we would have had a unique minimum. After crossing half of the values, the slope of the sum of distances becomes 0, and it doesn't change until we are crossing the next value. So if the next value at index n½ + 1 is different, any value between the two could be a median. Normally, this happens if our variable can take on many different values. The usual choice in this case is the value halfway in the 0 slope interval. Thus, we're taking the average of the 2 values in the middle of our sorted list. In our case, this gives us a median of 5. However, if we assume that our measured 6 was indeed a 4, then we would have again a V-shaped minimum at 4. If the next value after half the sorted values equals the one before, the median is again unique. This usually happens if our variable can take on only a few different values. In this case, the median could be each of the 2 equal values in the middle of the sorted list. For us, it is 4. Interestingly, we didn't get a formula to calculate the median. Instead, we got a procedure. First, sort all our values in ascending order, or we could also use descending order, and then take the value exactly in the middle, if we have an odd number of measurements. It's more complicated for an even number, so always avoid this problem by measuring an odd number of values. Now the sum of the distances is not the only way to consider all distances. Another possibility would be to square the distances before adding them. Why would anyone have such an outlandish idea? Well, if we square the distances before we add them, we have a sum of quadratic functions, which is again a quadratic function, and thus it is smooth. So it's much easier to find its minimum, and secondly, the minimum of a quadratic function is always unique. So our second idea for the middle is to minimize the sum of squared distances. For this, we can replace the absolute value bars by simple parentheses. Minimizing this sum will lead us to the arithmetic mean, or mean for short. Let's go back to our initial 7 values 7, 6, 3, 4, 4, 7 and 6. We choose some trial value, say 5. You'll see why in a minute. Instead of the distances from our measurements to this trial value, we now take the areas of the squares from our values to the trial value. Moving our trial value even a little away from somewhere in the middle, the areas of the squares can get very large. Now we can do our scan again. The sum of the squared distances starts out rather large, but decreases smoothly. There are no kinks when we are crossing one of the measured values. After going through the minimum, the sum increases smoothly again. The unique minimum is found at about 5.29 and is called the mean, denoted by x bar. As a reminder, the median of these values was 6. Thus our different ideas what to minimize give different middles. We now want to minimize the sum of the squared distances. There are several ways to do this, but we will simply look for the zero of the first derivative. Deriving with respect to the trial value x turns the powers of 2 into factors of 2, and the chain rule gives us an additional minus in front of every term. We can further rearrange this to minus 2 times the sum of all values plus 2 times n times x. Now we must find the zero of this expression. Since it is a linear equation, we will only find one zero and thus only one minimum. Dividing by 2 and rearranging, we get that the mean, x bar, equals the sum of all measured values divided by their number. In our case, this comes out to about 5.29. So far, we have used distance in the usual sense, but in mathematics that concept is more general and maybe a bit strange. This leads us to our third idea, minimizing the sum of discrete distances. We'll see in a minute what that means. This will give us the so-called mode. We start again with our 7 values, this time already in ascending order. And we'd like to minimize the sum of distances, nothing new so far. But this time, the distance will not be the usual geometric one. If our trial value is equal to a measured value, the distance shall be 0. That is the least we expect from a distance. However, if the trial value is different to the measured value, the distance shall always be 1, no matter how far away we are from the measured value. This is called the discrete metric, where metric is just a fancy word for being able to measure distances. How can we visualize such strange distances? Let's assume that our trial value is different from all measured values. Then the distance to all measured values is 1 in each case, no matter how far away we are. We will indicate this with distance bars of length 1. If our trial value equals one of the measured values, the distance to this value is 0 and it remains 1 to all the others. After crossing this value, the distance to it is again 1. The direction of the line segment is irrelevant. Now let's do our usual scan. As long as we are away from all measured values, each distance contributes 1 to the sum of distances. Thus our sum is essentially counting the number of measured values. Every time we are on top of a measured value, the sum of distances is reduced by how often this value occurs in our set of measurements. The value 3 occurs only once, so the sum is reduced by 1. The values 4, 6 and 7 occur twice each, and the sum there is reduced by 2. So we have 3 equal minima, and each one is called a mode. Thus a set of measurements can have more than one mode. Looking for the minimum, or the minima, of our sum of discrete distances is just an elaborate way to find the values appearing most often in our measurement. Or, if we have a lot of different values, we look for the intervals where the density is highest. Now, what does that all mean for the 3 examples we started with? In the first example, the density of our values was large in the middle and dropped off symmetrically to both sides. As mentioned, the mode here is that x interval with the highest density of measured values, that is, the highest bar in the histogram. The median is almost identical, and so is the mean. The 3 values are not exactly equal, but approximately. All 3 could be used as a measure for the middle, and most people would agree that this is also the typical value. In the second example, our values were distributed into 2 separate blobs. Because there are slightly more values to the left, the mode can be found there. Similarly, the median is also pulled in this direction. So it is not directly in the middle of nowhere, but close. On the other hand, the mean is almost exactly halfway between the 2 blobs. The mean might be better to describe our feeling for middle here, but all 3 values are pretty much useless. There's nothing much typical that could be said about all these measured values. The third example is a bit trickier. The density of the measurements is high to the left, but trails off to the right. Such a distribution is called right-skewed. The highest density interval is almost at the left edge, and that is where the mode is. The median lies solidly in the left half of the distribution because most values can be found there. The mean is larger, but not much. Which one of these three values is a better representation for the middle? Which one is, so to speak, more typical? There is no clear answer. It is up to you to decide which one is the best summary of your data. In right-skewed distribution, the median is usually less than the mean, like it is here. However, for the following, slightly construed example, the positions are reversed. But again, it's your decision whether the difference between the two is important or not. We started out looking for the typical value of a set of measurements, but we soon moved our goalpost and looked for the value in the middle. And depending on how we define the deviation from that value, we will get different answers. So which one is the correct middle now? Is it the mode, or is it the median, or is it the mean? And which one is more typical than the others? Unfortunately, there is no general answer. All of them are in some way correct, and none of them is definitely wrong. It depends on what properties you expect from your middle. All of them are what's called a measure of central tendency. So far, we've always spoken of measured values, but the mathematics doesn't care where our values come from. We are essentially discussing properties of sets of numbers. Finally, one often made point when comparing median and mean is that the mean is less sensitive to outliers. But this discussion deserves a video by its own.